plus the mass of the, what we call added mass. So this force can be thought of as an inertial force. Remember, when you move anything, when I move anything, you can think of it two ways. When you move this cup with an acceleration A, I need to exert a force that is in the same direction of the acceleration equals ma. Okay? But if this cup is magically accelerated with some source, it will experience an inertial force in the opposite direction equals ma. This is the inertial force. Okay? This is the exact same thing here. This is the force from the fluid to the solid. So if the solid is accelerating the fluid with some source, okay, now the fluid will respond back by its own inertial force, which is negative the mass times acceleration. You see what I'm saying? Okay, you can use the same principles to write down the pitching moment. I'll give you the expression. So this is the pitching moment at the hinge. U H dot AB H double dot U squared alpha negative B squared A squared plus 8 alpha double dot. Again, there is the concept here of added inertia. I added. Okay? Any question? So this is a very important relation in unsteady aerodynamics. Yes, Jeff?
Does this effect always happen, or is it dependent on the amount of acceleration that's being applied on the airflow?
You mean the mass?
Well,
I understand your intuition. For sure, the force depends on the acceleration. So there is one very important point here. Remember at the beginning we said, we will not accept any model that is not dynamical, in the sense you give me an input, there has to be some lag for the output to come, right? This equation is an algebraic equation. Yeah, it has some derivatives in the right-hand side, but remember what we discussed. This is an algebraic equation. You give me alpha double dot at this time instant, I give you lift at this time instant. This is an idealization, of course, according to the potential flow. So within the framework of potential flow, this is an idealization. If you introduce viscosity, you will immediately get lag. And this is what Amir showed in using CFD simulations. So this is one thing, is that always in the back of your head, the non-circulatory loads, you can easily represent them by algebraic equations. Okay? They don't need dynamical system representation. Of course, this is not very accurate, but it's an acceptable approximation. This a little bit answer your question, or is not related?
Yeah.
So, related to your question also, is this really constant? Because look at this equation. It's also intriguing in the sense that, well, give me your acceleration at the half-core point, I give you the lift, and the proportionality constant is fixed. It's just related to the geometry of the airfoil, half-core. That's it. It's interesting. So if you do that with any frequency, with any speed, if your acceleration is very, very high, will it be the same mass? So this is another research question. Well, it's fixed within the realm of this analysis, which means for a small angle of attack, large frequencies, that's fine, but still, because remember, if you do large frequency, you're affecting the effective angle of attack. The normal speed here, what's the angle of attack? The angle of attack is the normal speed divided by U infinity, right? So I can have a small alpha, but when you have large frequency, omega, large, this guy, if h is sine omega t, h dot will be omega cosine. So this guy has omega in it. So if you increase omega, even with a small angle of attack or a small amplitude here, but it's proportional with omega, so it will increase the effective angle of attack. But if you can do it with high enough frequency such that the effective angle of attack is small, this is a reasonable approximation. When you do this, sometimes we do the frequency response even with simulation CFD. So this is the amplitude of the lift with frequency, and we find this relation. It's quadratic in frequency. Why quadratic? Because it depends on the acceleration. The acceleration is quadratic in frequency. It's omega squared. We really find this using CFD even with viscous simulation tools. It's doing it. Okay? So this is in some sense, it's a good approximation for the non-circulatory lift. It's not as bad, but still there is some room for enhancement if you plan to. Okay, see you Wednesday.